Here we're going to look at two examples of surface integrals of vector fields. But before we do that, let's recall the setup. So we derived kind of the meaning of a surface integral of a vector field earlier, and that led us to the following observation. So I'm sweeping some stuff under the rug, like is it an orientable surface? What are the hypotheses regarding F and stuff like that? So we'll just assume that F is nice, the surface is nice, and everything else. So if R, U, V parametrizes the surface where U and V come from D, which is a subset of the real plane, then the surface integral of the vector field F, which we generally denote as this integral S F dot ds, so that can be shown to be equal to this just plain old double integral from much earlier in the course. So this is the double integral over D of the vector field dotted with this thing RU cross RV, where those are made up of partial derivatives of our parameterization, and then dA, again just a plain old double integral. Okay, the example we want to look at first is this F dot ds of our vector field F, which is 0, minus z, y, and then our surface is the unit sphere in the first octant. Okay, so let's go ahead and draw a picture of this, which is not super necessary because this is a pretty simple surface, but it's always good. I think it's good to draw pictures because it turns on the creative part of your brain, which is super important for math, maybe more important than anyone thinks. Okay. Good. So the unit sphere in the first octant, maybe I would draw that like this. So that's going to be just like that portion of the sphere right there. So notice we could maybe draw lines on it like that so it looks more spherical. So it's 1/8 of a sphere. And now notice I said it's a unit sphere, so we can write this as 1, 1, 1. Okay, so as I see it, there are two standard parameterizations that we could take. We could take a rectangular parameterization, and that would look like this. We could say that the sphere is the equation x squared plus y squared plus z squared equals 1, which tells us that we can take z equal to the square root of 1 minus x squared plus y squared. Notice we don't need plus or minus the square root because we're just in the first octant, which is above the xy plane, so the z values are positive. And then here, x and y would be in, well, I'm just going to draw a picture of it. So they're in this portion of the xy plane. So it's the first quadrant of a disk with radius 1. Okay, so that would be one way to parameterize it rectangularly. So we would just take r of x comma y to be equal to x comma y comma the square root of 1 minus x squared comma y squared. You know what? And that might totally work easy enough, but I'd rather do a spherical parameterization. And that is going to take inspiration from spherical coordinates. So let's go ahead and recall what spherical coordinates look like. So we have x is equal to rho cosine theta sine phi. We have y is equal to rho sine theta sine phi. And then we have z is equal to rho cosine phi. So that gives us spherical coordinates, but that draws the whole region R3, but we only want to be on the sphere. Furthermore, we only want to be on the sphere in the first octant. So to put us on the sphere, what we'll do is just go ahead and take these rows, which were variables, and set them all equal to 1. That's just going to mean that we're always 1 unit away from the origin. Great. And now we'll have r of theta comma phi is equal to, let's see, we've got cosine theta, cosine phi, sine theta. And then we've got this nice form for our parameterization. So r, theta, phi are our variables. So we've got cosine theta, sine phi, and then sine theta, sine phi, and then finally cosine phi. Fantastic. And maybe we want to talk about where theta and phi live. So notice theta is going to live between 0 and pi over 2. That's going to keep us from the positive x-axis to the positive y-axis. And then phi is also going to go between 0 and pi over 2. Remember, phi measures from the positive z-axis. That's going to take us from the positive z-axis down to the xy plane. Okay, great. Now the next thing we need to do is calculate r theta cross r phi. So we'll use our matrix determinant formula for that. So let's do the I component first. So let's see, the derivative of this with respect to theta is going to give us minus sine theta sine phi. The derivative of this with respect to phi is going to give us cosine theta cosine phi. So that's what we get under the I component. Now under the J component, we're going to go ahead and get cosine theta sine phi, and then we're going to get sine theta cos phi. Okay, great. And then under the K component, we have the derivative of this with respect to theta, which is 0, and then minus sine phi. So we get something like that. Okay, great. Now let's go ahead and see what we get here. So in the first component, we'll get whatever happens from crossing here and taking the 2 by 2 determinant. Notice that is going to give us a minus cos theta sine squared phi. Great. And then times, minus something times 0, so we don't care about that. And then in the J component, we'll get whatever we get from taking that determinant. But notice we have to add a minus sign in from the calculation formula. That's going to be minus sine theta sine squared phi. So minus sine theta sine squared phi. That's what we get there. And then in the K component, which is what we get from taking the determinant of this 2 by 2 that's left over, we'll get sine squared theta. So I'll put this down here because we're running out of room. So we have sine squared theta from multiplying that and that times sine phi cos phi. And then that has a minus sign attached to it. And then we have minus cosine squared theta times the same thing. But if we have minus cosine squared theta times the same thing, we can combine those things together into 1. And that just gives us minus sine theta sine phi. So that's our third component. So this is a little bit messy, but this is our first, second, third component. Okay, I'll clean up the board. I'll bring that up and then we'll continue. We've got this parameterization r theta phi, so cosine theta sine phi, cosine phi, and then we have r theta cross r phi is this object right here. Now here's something to be careful for. If the problem tells you whether your parameterization should be oriented in one direction or another, you have to be careful, because notice this normal vector is oriented back in that direction. So if you're along the sphere, it's pointing towards the origin, whereas you might want something that's pointing away from the origin. So we'll just go with this and notice that this is pointing towards the origin. In other words, it's pointing in. Now that being said, we can fix it to point out just by changing everything to a minus sign. And so that's just going to change the sign of the final answer. But then again, you'll just have to look at what the problem says, and does it specify an outward facing normal or an inward facing normal? And this is an inward facing normal. But if we wanted an outward facing normal, we just negate the whole thing. Okay, so now we can go ahead and do this using this observation over here. So let's see, maybe I'll go ahead and call this thing I for our integral that we want. Now we have I equals, so this is going to be the double integral over d, but we know what that is. That's going to be 0 pi over 2 for theta and phi. And then we have our vector field, which is 0 comma minus z, but minus z is minus cosine phi. And then we have y, but y is this thing right here. So sine theta sine phi. Great. And now we need to dot that with this thing right here, r theta cross r phi. So let's go ahead and see that. Notice we have a 0 in this first component, so it doesn't matter what this is. So I'll go ahead and write star here because we don't need to include that first component. And it's rather lengthy, so that's going to actually help us. So now we have minus sine theta sine squared phi, and then finally minus sine phi cosine phi. So that's what we get. And now let's just say that here we're going to do d theta d phi. Although, like I said before, it doesn't matter what order we do this in. Okay, so now moving this over here, we're going to have the double integral 0 to pi halves, 0 to pi halves. Now we have to go ahead and do this dot product. So we've got that dotted with that, so that's going to give us sine theta, and then sine squared phi times cosine phi. Notice some of the minus signs cancel, so that's good. Now let's see what we get for the next part. So we'll have this sine theta sine phi dotted with that. So that's going to be minus sine theta. And then we'll have sine squared phi times cosine phi. Something like that. Okay? And then finally, we have d theta d phi is left over. Oh, but look at what's going on here. We have the same thing in each component, which just tells us this whole thing is 0, because notice these things cancel. So we're good to go. Okay, so that finishes this example. I'll clean up the board and we'll look at one more. For our last example, we're going to look at this. So it's the surface integral of the vector field f, which is given by xy comma minus y comma 1. And then our surface is this paraboloid upward facing that is below the plane z equals 4. So let's go ahead and make our picture. So let's say we've got our x and our y and our z axis here. So let's see, like I said, this is an upward facing paraboloid. So in both directions it looks like a parabola and it opens like a circle. Good. So we've got some picture like that. Let's go ahead and say that this is z equals 4. So I'll put a 4 here, which makes this kind of ridge around here 2 units away from the origin. In other words, if we project this thing down to the xy plane, we get a circle of radius 4. And that circle of radius 4, or I should say the disk of radius 4, is going to be d, which parametrizes this surface. So, like I said, we need to look for a parameterization of the surface, but since this is given by z as a function of x and y, that's quite easy to do. We can just do rxy equals x comma y comma z, which is x squared plus y squared. And then we can also go ahead and use just this thing as our region. So I'll just say d equals this. So I'll go ahead and put a 2 here, and this is going to be a disk of radius 2. Or we could write this in a set form as x comma y, such that x squared plus y squared is less than or equal to 4. That just screams to use polar coordinates later, which we might do if it seems advantageous at the time, but I'd say it probably does seem advantageous. Okay, so we need to go ahead and calculate rx cross ry. So let's see what we can get for that. So let's see, in the I component, the J component, and the K component, let's just do this as we do it. So we'll have Rx in the first row, Ry in the second row. I should say second and third row. So the derivative of this with respect to x is 1, 0, and then 2x. And then similarly 0, 1, and then 2y. So it's nice, easy partial derivatives. Now let's see what we get for that. So in the first component, that's going to give us minus 2x. Then in the second component, that's going to give us minus 2y. And then in the third component, that's going to give us 1. So there's actually a pretty common formula for special cases when we have z equals a function of x and y that you can look up in your textbook if you want and just use that. Okay, so there's what we get for rx cross ry. Now let's go ahead and calculate this integral. So we have I is this double integral over d, again using this observation over here. And then we've got f, which we can go ahead and use our original variables, so x, y, minus y1. Now I should say, if there were a z in this vector field, which there is not, but if there were a z in this vector field, we would use this for the z, because that takes the z component in the parameterization. Okay, so we've got that. That's our vector field dotted with rx cross ry, which is minus 2x, minus 2y, comma 1, and then dA. Okay, so let's see what that's going to look like. So we've got the double integral over d, and then we're going to have minus 2x cubed y. And then let's see, minus 2y squared. And then finally, plus 1. Good, and then dA. Okay, so I'll go ahead and move that up, and I'll say that we'll probably move this to polar coordinates as well. Okay, so we worked the surface integral down to this nice simple double integral over this disk, so we probably want to change to polar coordinates. So let's just recall, in the change to polar coordinates, we said x equal to r cos theta, y equal to r sine theta, and then that means dA becomes r dr d theta. Great. And then notice that our region D can be expressed in a much simpler way. So notice here we have R running between 0 and 2 because that's the radius of this disk. And then we have theta running from 0 to 2 pi. Again, because we have the whole picture here. All right. So let's see what we get for that. So that's going to be the integral from 0 to 2 pi, the integral from 0 to 2. Now we have minus 2 r cubed cos cubed theta sine theta. Okay. And then minus 2r squared sine squared theta, and then plus 1. And then let's see, we've got dr d theta, and then we've got an extra r in there. Okay, so let's go ahead and take this extra r that comes as part of the dA, and we'll distribute it in. So that'll put us a plus r here, that'll put us an r cubed here, that'll put us an r to the 4th here. Okay, so that's going to give us the integral from 0 to 2 pi. Now let's go ahead and take the antiderivative of that with respect to r. So that's going to be minus 2/5 r to the 5th cos cubed theta sine theta, like that. And then we have minus a half r to the 4th sine squared theta. Okay, good. And then plus 1/2 r squared. Now we're evaluating that from 0 to 2, and that's r equals 0 to 2, and then we have a theta integral in the end. Okay, so let's see what we get for that. That's going to be the integral from 0 to 2 pi of, so let's see, that's going to be 32 times 2 is 64 over 5, so we have minus 64 over 5 cosine cubed theta sine theta. And then here we're going to have 2 to the 4th, which is 16 divided by 2 is 8. So that's going to be minus 8 sine squared theta. And then plus 2. And then we have d theta in the end. Now I'm going to cheat a little bit. It's not really cheating, but notice here we would do a u substitution where u equals cosine, so that's going to make that u cubed, and this is going to be minus du. So notice the antiderivative of this is going to be like cosine to the 4th, but if we evaluate that from 2 pi and 0, we'll get the same number because the period of cosine is 2 pi. That's going to make this whole thing go to 0 in the integral. So I'm just going to go ahead and skip that because we don't need it. And then furthermore, we can take this and use a trig identity. So this is going to be minus 8 over 2 times 1 minus cosine of 2 theta. So let's see, that's going to give us the following. So now we have the integral from 0 to 2 pi. And then let's see, we have minus 8 over 2, which is like minus 4, plus 2, which is like minus 2. So we have minus 2. And then we're going to have plus 4 cosine 2 theta d theta. Okay, but now if we take the antiderivative of cosine, we'll get sine. Again, evaluating at 2 pi and 0, those will both give us 0. So this part is just going to cancel out. So really we just have the integral of -2 from 0 to 2 pi. That's going to give us minus 4 pi. Okay, good. So I've skipped some details, but they're like calculus 1, calculus 2 type details. So work through them if you feel like you need to, but I think we're okay here.